We'll talk in this video about capacitors and inductors. Capacitors and inductors. We will start with the capacitors. What is a capacitor? It's two plates, conducting plates. You connect these two plates to a voltage source. That voltage source will charge the capacitor with plus Q and minus Q. And units of capacitance is in farad, and it's known as capacitance is Q charge divided by V. So it is charge divided by voltage will give you farads, abbreviated as F. Okay, this is basically the law of capacitance. So from this we can say that Q charge equals C times V. In fact, the current I is equal to C dV per dt. So we take it I dt equals C dV. So if we integrate both sides, we'll get here charge equals C times V. So these are the basics of capacitors. So a capacitor, you charge it with charge Q using a voltage source V, so it will store energy. So let's look at the stored energy. Stored energy of a capacitor is equal the voltage times the current, and we integrate that with respect to time, which is equal C V dV per dt times dt. This will give you integration of C V dV, so it will be half C V squared. So the energy stored in a capacitor will be half C times the voltage squared. Energy is stored as electric field. So we know now the capacitor does not dissipate energy, it stores energy as electrical field. So let's look at how we connect capacitors together. Capacitor connection. We have parallel and series. Let's look at the parallel connection first. So we have few capacitors connected in parallel. When we connect capacitors or elements in parallel, we connect them all together across two nodes. This is node 1 and this is node 2, which means that all the capacitors having the same voltage. So if this is C1, this is Cx, this is Cn, then C1, C2, Cx, Cn have the same voltage. So if we assume that the voltage will supply a total charge Q total that will be distributed among all of them, Q1, Qx, and Qn. So if we apply KCL, Kirchhoff's current law, to node 1, what we will get? I total is equal I1 plus I2 plus Ix plus In. Now, if we multiply by dt and integrate, what we will get? I total dt is equal I1 dt plus I2 dt plus Ix dt plus In dt. Now, if we integrate both sides with respect to time, we'll get here integration of I total dt is Q total is equal to I1 dt is Q1 plus Q2 plus Qx plus Qn. So the total charge will equal to the sum of all individual charges of the capacitors. Now what is the Q total? If we substitute this with a single capacitor and we call this capacitor C total, you apply the same voltage and you charge the capacitor with the Q total. So this is an equivalent circuit or equivalent capacitance. Okay. Now, if we apply Q total as equal to C total times V is equal Q1, which is C1 times V1, and V1 is equal to V. V1, V2, up to Vn, all have the same voltage, which is V, because they are connected in parallel, plus C2 V plus Cn V, which means that C total is equal C1 plus C2 plus Cn. So C total is equal to the sum of the capacitors. So if we have parallel connection of capacitors, then the total capacitance is the summation of all individual capacitors together. Okay. How we determine Q1, Q2, Q3? Just you use the relationship between Q and C and the charge. Q equals C times V. So the charge is equal to the capacitance times the voltage. So this is basically the connections in parallel. Let's look at the connections in series. Series connection. In a series connection, we connect the capacitors in such a way that the same current or the same charge flows into them. So we have C1, C2, Cx, Cn. We have the same current I flowing in all the capacitors. So you have I, and if you integrate I with respect to time, you will get Q. So we're talking about the current or the charge, it should be the same. So if we apply KVL to this loop here, apply KVL, what we will get, V equal V1 plus V2 plus Vx plus Vn. So the sum of all the voltages across the capacitors will equal to the total capacitance. So we now transform this circuit to a single capacitance and we call it C total. C total, you apply plus minus V, you get Q total. Now, I1 is equal to I2 is equal to Ix is equal to In because they are connected in series, equal to I, which means that I1 dt equal I2 dt equal I dt is equal to Q. So it means Q equal to Q1 equal to Q2 equal to Qn. So if we have a series connection, then the charge across all capacitor should be the same. Only the voltage will sum to the total voltage, which is V. Now we apply this. What is V? V is equal Q divided by C. So V total, V is equal, this voltage here is equal Q total divided by C total. So Q total divided by C total will equal to the sum of all these voltages. V1 is Q total divided by C1. Why? It should be Q1 divided by C1 because the Q total is equal to Q1 equal to 2. So all the charges across the capacitors are the same. So this will be plus Q total divided by C2 plus Q total divided by Cn. So what we will get, 1 over C total is equal 1 over C1 plus 1 over C2 plus 1 over Cn. Or 1 over C total is equal to the sum of 1 over C's. Okay, the sum of all of them. So let's say from J equal 1 to N, so Cj. Okay, so this is the basic law of capacitors connected in series. So once we know the voltage, we can calculate the charge, or if we know the charge, we can calculate the voltage distribution among the capacitor. Let's look at some examples. Example. Let's have two capacitors in series with another capacitor, and we have a voltage source here, plus minus, let's say 100 volts. Let's have here 100 microfarad, and here is 200 microfarad. Let's have 600 microfarad. We want to know, determine charge across all capacitors. Two, voltage across all capacitors. Three, stored energy. Okay. See, let's look at this example. How we solve it. As usual, if we want to calculate the total capacitance seen by the source, so you have 600 here microfarad, 200 microfarad, and 100 microfarad. So we want to calculate what is C total seen by the source. We start as usual, same in the resistors. We start from the far end. So this is the far end here. So what we have here, the 100 and the 200 are connected, microfarad, connected with the 200 microfarad in parallel. So these two capacitors are connected in parallel, so it will give you Cx, which is equal 200 plus 100 equal 300 microfarad. So this we can replace it with Cx equal 300 microfarad. Now this Cx here between these two capacitors, between these two nodes here, okay, we replace them by Cx. And then this is connected with the 600 microfarad in series. And we want to find what is C total. Okay. Now Cx and the 600 are connected in series. So 1 over C total is equal 1 over 600 plus 1 over 300, which is equal 600 times 300 divided 300 plus 600. So 300 plus 600, which is 900, divided by 600 times 300 will give you what? 200 microfarad. So this is equal 1. This is equal C total, or equal 1 over C total. So 1 over C total, 1 over, okay, times this. So it's not microfarad, 1 over microfarad. So what is C total? So what we have here is 300 plus 600, 900 divided by 600. So this figure is not correct. This is wrong, never mind. So we can keep it as it is there. So C total will be 600 times 300 divided by 300 plus 600. So we don't need actually to calculate this, because we will take the reverse of that to calculate C total. So this, what we have calculated here, this here is 1 over C total. So C total is just the reciprocal of that. So this will be 1,818,000 divided by 900, 300 and 600. So this will be 1 and here is it 2? So you'll get 200 microfarad. So that's C total. That's the first step. So first, to calculate C total, we do it the normal way. We start at the far end. They are connected in parallel. Then we calculate Cx. Cx is connected with the 600 in series, so we calculate C total. Now, we know the voltage. We know C total. So what we have here, C total, and we have the voltage source, V equal 100 volts. So we can calculate now what is Q total. This is Q total. Q total will be C total times V. So it will be 200 microfarad. So times 10 to the minus 6 to convert it to farad, times the voltage 100. So that will be 100, and 100 here is 10 to the power 4. So it will be 2 times 10 to the minus 2 coulomb. Okay? So that's the total charge of the total capacitance, or supplied by the voltage source. Now, so if you look at it here, that's the first step. Now we have to calculate the charge for each capacitor. Okay? If you look at it, this is the charge, total charge. 600 and Cx are connected in series, so we have the same charge. This 0.02 coulomb, this charge here is the same as the charge of the 600 microfarad as well as Cx, which is the 3, because they are connected in series. This means that the charge is the same. So simply we can say that according to this, so I will just draw them again here. Cx equal 200 microfarad, and here we have the 600 microfarad. So here we have Q total. So we can say Q, the 600 microfarad, is equal Q total equal 0.02 coulomb, right? Similarly, Q of Cx equal Q total equal 0.02 coulomb. So, because they are connected in series, so Q total is the same as Qx here. So you have here plus minus Q total, and here we have plus minus Q total, because they are connected in series. So once we know the Q, we can determine the voltage. What is the voltage of 600 microfarad? Will be Q 600 microfarad divided by C, which is L 600 microfarad. So Q is 0.02 coulomb. And C is 600, but we must convert it to farad, so it's minus 6. So this will be 0.02 times 10 to the minus 6 divided by 600. So it will be 0.02 times 10 to the minus 4 divided by 6. Right? So this will be how much? How you calculate it? Sorry, here we have the mistake. Here minus 6, here would be plus 6, right? Okay, bear with me. So divided by 600, here will be plus 4. Sorry about that mistake. So we remove 100, remove 100 from here. So this will be 2 over 6. This will be 2 times 10 to the power 2 divided by 6. So you get 200 divided by 6, which is 100 divided by 3 volts, which means 1/3 of the volts will be applied across the 600 microfarad. From this, we can calculate also, using the same procedure, Vx. This is Vx, the voltage across capacitance X. We can say it's 0.02 divided by 200 micro times to the power minus 6. So it will be 0.02 times 10 to the power 6 divided by 200. So this will be 0.02 times 10 to the power 4 divided by 2, right? So it will be 200, right, divided by 2. So that will be 100 volts. 50, sorry. Yes, 100 volts. We should, is there a mistake here? 200, charge 0.02, 100. There must be a mistake here. Sorry, there's a problem here. Yes, Cx is not 200, sorry. Sorry about that. C total is 200. So Cx here was 300, right? That's why if we get here 100, it means we have a mistake. This is 300. So let's correct that. So this is 300, this is 300, this is 3. So what we will get here, 200, 2 over 3 times 100 volt. So if we compare here, and this one, we see that the sum of them, Vx plus V600 microfarad equal 1/3 plus 2/3 of the 100, so it will be 100. So we are correct in this case. So the sum of both voltages will be 100. So what we have here actually plus minus 100 volt. Always you check your answers. You'll discover the mistake here. Okay. So 1/3 of the 100 will be across the 600 microfarad, and 2/3 of the 100 will be across the 300 microfarad. Now, we want to calculate individually what is the individual charge and voltage across each capacitor. So what we have here is 100 original microfarad, and what we have here is 600, 200 microfarad. Okay, so this is actually Cx, which is equal what? 300 microfarad. Okay, now what we did actually, we have calculated Cx. Now if we look at V 200 microfarad equal V 100 microfarad, because they are connected in parallel. So we can calculate the individual charges. So Q200 microfarad is equal 200 microfarad 10 to the power minus 6 times Vx, which is 2 times 10 to the minus 4 times Vx, which is what? 2/3, 2/3 times 100 volt. Okay, 2 times 2 is 4, and here 100, so times 10 to the minus 2 divided by 3 coulombs. Same for the Q, 100 microfarad. You do the same. So 2 times C, which is what? 100. Times 10 to the minus 6, that's 100 microfarad times Vx. So it will be 1 times 10 to the minus 4 times 2/3 of the 100, right? So you'll get what? Okay, 2/3.02, is it? Let's say 2 times 10 to the minus 2 divided by 3 coulombs. Okay. So we know how we have calculated the charge and voltage. Okay, here is the charge and voltage of all capacitor 100, 200, and we have also, don't forget that, the 600 microfarad. So what is left? We have what is left from our requirements? One charge, voltage, we have calculated them. Now stored energy. Just apply the law of the energy, which says that a W stored in an energy half C times V squared. So, what is the stored energy in the 600 microfarad is equal half C, which is 600. We convert it to farad 10 to the minus 6 times V squared. So what was the V600? V600, as we have calculated, is 100/3. So times 100/3 squared, and you can calculate how much. Okay. You can do that easily. It's equal here half and here 9, so 1/18. 2 times 9, 18. Here is, let's say, 600 here, okay, times 10 to the minus 6. Here squared times 10 to the power 4, right? So here 100 and here 10 to the power 4, that will be 10 to the power 6, so it will be basically 6 out of 18, which is 1/3, right? Okay, so that will be the stored energy and the capacitance. Okay, 2 times 9 is 18, 600, 10 to the minus 100 squared, 10 to the power 4, and here you have 10 to the power 2, will cancel with the 10 to the power 6 out of 18. The unit is joule. Okay, now to calculate the stored energy in the originally what we have here, the 100 and the 200. So the stored energy in the 100 microfarad is equal half times 100 times 10 to the power minus 6 times the voltage, we have calculated, which is 2/3 Px 2/3 times 100, so 200 squared. So that will be 3 times 3, 9. So again, here we have 18. Here 2 times 2 is 4. Here 10 to the power 10 to 400 times 10 to the power minus 6 times 10 to the power 4. The 100, the 2 is 4 outside, okay? So that would be 4/18, which is equal 2/9 joule. Now we calculate the stored energy of the 200 microfarad, which is equal to half times 200 times 10 to the power minus 6 times the same voltage, which is 200/3 squared. So that will be 18. 2 times 2 is 4, times 2 is 8. 100 times 10 to the power minus 6 times 10 to the power 4. So that will be 8 divided by 18. So it will be 4 divided by 9 joules. Okay. Now let's sum them, add them together. What is it? DW600 plus the stored energy of the 100 microfarad plus the stored energy of the 200 microfarad. This will be 1/3 plus 2/9 plus 4/9. So that will be 9. Here we'll get 3. Here we get plus 2, plus 4, so 6. So it will be what? 1. 4 plus 2 is 6, so it will be 1 joule. Now, why we did that? We want to compare it with the stored energy of the equivalent capacitance. What we have C total here. C total equal what? C total we have calculated. C total equal to 200 microfarad, right? 200 microfarad. And we have the voltage source here, 100 volts. And we have Q total here. So there is stored energy. The value total. Okay. Which is simply half C total times LV squared. So what we have here is half C total is 200 times 10 to the power minus 6 times the voltage, which is what? 100 squared. So this will be 2/2. So 100 times 10 to the minus 6 times 10 to the power 4. So it will be what? 1 joule. So you see, if we add the energy of all capacitors together, it should give you the total energy, which is the same energy as stored in the total capacitance. And always you check that to make sure that you have the right answer. Okay? So I will end up the capacitors at this stage, and for the next video shot we'll talk about the inductors. Okay? Good.